Good morning. Today we will discuss about the thermoelectric generator, the module and device configuration, and the power generated by the thermoelectric device and different application of thermoelectric devices. So what we have studied so far is that what are the important properties of materials required for a good thermoelectric generator. And what we have seen that there are several materials. We started with some conventional materials, and then we have seen some nanostructured materials. We have discussed about a typical material class which is known as PGAC material, and then very low dimensional material like two-dimensional quantum well. So what we have seen overall that when we use these materials in thermoelectric generator, we keep in mind several factors. So the first and the most important factor is figure of merit. So it is extremely important that when we make a device or thermoelectric generator, one needs to optimize that figure of merit. Apart from that, power factor is also there, which we have discussed, and then efficiency of a thermoelectric generator or thermoelectric device. Okay. So all sorts of the investigations of material are broadly depends on optimization of all these parameters, and this is what we have discussed, taking several examples. So now let us again look at how one small thermoelectric module is made, which I have already discussed, but sake of completeness I will again discuss it now. And you can see that when you consider a semiconductor based thermoelectric generator or a single module of a thermoelectric generator, we basically see that there are two types of semiconductor, P type and N type. They are called thermoelectric elements. They are also known as LEDs for a thermoelectric device. Okay. So we have some heat source from where heat comes, and there is a heat exchanger, and then we have heat sink, and there is another heat exchanger here. So what we have created here is a high temperature TH and a low temperature TC. Okay, and the temperature difference basically generates a thermo EMF. That is what we know. And then for this module, it is connected with a load outside, where we determine the power, or the how much power is delivered to this load. That is what we calculate. Okay. So now, if you remember that we have discussed about the figure of merit, which is equal to, when we consider such case, when we have one N type and one P type semiconductor, the figure of merit is okay. So it depends on both the Seebeck coefficient alpha p and alpha n of both P type and N type semiconductor, thermal conductivity Kp or kappa p and kappa n, and also electrical conductivity sigma p and sigma n. Okay. And now if we have a length of the leg, considering the geometry of the thermoelectric module. So, I have, this is the length of the leg of the TE leg, say for this is for the N type, and this is the area of say for the N type, and similarly we have length LP and area AP for P type. Then geometrically one can show that how this length or the geometrical parameters like length and area depends on the real physical quantities like electrical conductivity and thermal conductivity. The thermopower value is very small, few hundred microvolt, that is what we have seen. And now if you take a semiconductor, thermoelectric or thermocouple, then it is improved little bit, because we know that the figure of merit in case of semiconductor are optimized, but still it may be some millivolt per Kelvin. So, it is not a very a device which can generate an appreciable amount of voltage, or it just generates small voltage. So, it is extremely important that we have to connect such a thermoelectric module in order to make or a proper device which can deliver an appreciable amount of power to the circuit. Okay. So, when we design a thermoelectric generator, then we have to consider this particular thing. Okay. And therefore, in a real thermoelectric generator you can see that there are series of such modules are connected. So, we have NP, a series of modules which are connected, and this is the hot side, okay, and this is the cold side. So, this is the hot source, you can say, or this is the sink which is cold. Okay. So, all these small modules are connected in order to get an appreciable amount of voltage output. Okay. So, there are some other geometrical parameters which are important. So, capital L is basically the length of the leg, that means the length of the P type or N type semiconductor that just now I have discussed, and LC here and here are basically very small, the contact length where they are connected, the modules. Okay. And now when we have such series of device, then one can show that the voltage output of this device actually depends on Seebeck coefficient, it depends on number of legs. So, alpha is Seebeck coefficient, n is the number of legs, delta T is the temperature difference, okay, and kappa is, anyway we know that it is thermal conductivity, kappa C is the contact, the thermal conductivity of the contact material, and capital L is annual length, and LC is the contact length, and L, I must mention, is the length of the okay. So, it depends on all these parameters, the voltage output. Similarly, if we look at the current, it also depends on alpha, that is Seebeck coefficient, sigma is electrical conductivity, A is the area, and delta T, and then rho C is the contact, the resistivity, electrical conductivity, okay, and all these quantities. Okay. This can be analyzed. I am not deriving it. This can be analyzed and can be found in the literature. Okay. So, the power output of such generator having n number of the modules of n number of legs, it depends on again on the Seebeck coefficient, electrical conductivity, area, number of legs, difference in temperature. Okay. That means Th minus Tc, it depends on contact, resistivity, electrical conductivity, length of the leg, thermal conductivity of the contact material. Okay. So, all these quantities actually contribute to the power output of a thermoelectric generator device. Okay. So, if you look at this particular the expression, this clearly shows that it depends on the power factor alpha square sigma. So, you can see P depends on power factor alpha square sigma, it depends on the area, okay. It depends on the number of legs, it depends on temperature difference, and they are not all directly proportional. Okay. So, if I have higher power factor, I have a higher power output, okay, and all these quantities will optimize the output power, and it also depends on the resistivity of the contact material, resistivity, conductivity, thermal conductivity of the contact material, length of the legs, and also length of the contact materials. Okay. So, now if we look at the how the power varies when we consider a real thermoelectric generator device. So, along x axis we can plot the temperature and the y axis is power density. Okay. That means the power generated per area, unit area, it is in milliwatt per centimeter square. So, several thermoelectric generator devices based on the conventional material. We know the conventional material are barium, bismuth, telluride. Okay. Conventional material is bismuth telluride, silicon germanide, etc. So, if I look at the bismuth telluride, and typically if I take a ZT value of about 0.9, then I can have a maximum power density. Okay. And if you take silicon germanide with ZT is generally low, 0.11, then I have the other end. This is the variation of power density with the temperature. Okay. And the red one is again BIT with ZT 0.6, and the black one, dotted one, is silicon germanide with ZT 0.26. Okay. So, all these quantities which we have discussed in the previous equation basically affect in a combined manner and gives the output power of a thermoelectric generator. All right. So, Now again going back to the material issue. So what we had discussed earlier is that when we want to make a thermoelectric generator device, we have to optimize the material, like optimization of figure of merit, power factor, etc. And then I also discussed broadly about nanostructured material. Okay. So let us just look at this particular silicon nanowire, how it gives the improved figure of merit. Okay. So if you look at this particular analysis theoretically which has been done and look at the figure of merit here, you can see, so this is a figure of merit which one can consider from the bulk. This is a figure of merit if we consider 2D well, and this is a figure of merit and quite enhanced when we consider nanowire. Okay. So that means if we reduce the dimension further, we have a higher the confinement probability, and when we have higher confinement, it leads to higher ZT because there is an enhanced density of state, that is what we have already discussed, and also the probability of phonon scattering. So in the previous class we discussed about how phonon scattering basically contribute to the figure of merit, and particularly this contributes to the thermal conductivity due to lattice, which eventually contributes to figure of merit. Okay. So if you look at this particular case, then we can see that when we go to nanowire geometry of a thermoelectric generator device, or make a thermoelectric generator device with nanowire kind of material, then we have an enhanced ZT. In fact, one can also think about nanotube one dimensional structure. In nanotube structure, the advantage is that there are enhanced scattering from the inner surface as well as from the outer surface. Okay. And lot of investigations are going on for this this type of structure, one dimensional structure, for the improvement of ZT or figure of merit. Okay. So one example which shows here that there is a typical the nanowire, and it has grown by the technique which is known as the vapor transport technique and the electrolysis technique. And if you see that this is a typical the value of of the thermal conductivity, where we can see that thermal conductivity is lower, much lower when we consider the carbon nanotube or one dimensional nanostructure or nanowire. Okay. So and I already discussed that why there is an enhancement in the scattering and also reduction in the phononic part of the thermal conductivity. And now if we look at the ZT value, and if we compare this one and the red one, there is quite a bit of enhancement in the ZT value. Okay. So now this is one particular type of low dimensional material which are being used in the thermoelectric devices, and another low dimensional material which are used in thermoelectric generators or thermoelectric devices are superlattice. Okay, quantum dot superlattice. So what people have done in this type of structure, they have actually taken one particular material as a matrix, and then they have grown another material as the dot, quantum dot, and then you generate the layers. Okay. So you can see that this is one particular two layer the lattice, where these are the length dimension Lx and Lz, and W is the width of the well. Okay. So when we have this particular configuration, and I repeat it, okay, over various layers, then we get a superlattice structure which is quantum dot superlattice. And I have already discussed that when we have a sort of two-dimensional structure, what are the factors that contribute for enhancement in the ZT value? Okay. So, one is the enhancement in the electrical conductivity, because one can have modulation doping, which I have already discussed. There is an enhanced density of state, okay, because of asymmetry in the density of state. Okay. This is what we have seen, and then also of course the phonon scattering. So, any kind of the nano inclusion which we discussed earlier leads to enhancement in the scattering process of phonon, and which eventually leads to enhancement in the ZT value, and that is what we see here. So, there is a temperature temperature versus ZT, this temperature versus ZT value. So, you can see that you have a clear enhancement in the figure of merit here, and the figure of merit goes quite high, 2 or more than 2, and this happens just by changing the concentration of the quantum dots. Okay. So, when we had this quantum dot in the superlattice structure, the electron motion also depends on another process which is known as quantum mechanical tunneling. Okay, because there are the electron moving from one quantum dot to another quantum dot through the matrix by the process of tunneling. So, that also gives an enhanced parameter. Okay, and one has to have the optimum number of quantum dots. This particular case was taken for a silicon matrix where germanium quantum dots were grown with different concentration, and for certain optimum concentration we can see that there is a huge increase in the figure of merit. Okay. So, these are very the very recent progress in the design of the material for a thermoelectric generator, and if we look at an overall picture of the materials which are being used for electrical generator, then one can see this particular table. So, you can see that I already discussed with you about the scooterite material. Okay. So, if we look at the series of scooterites, okay, of different all the carrier types are n, and then one can have a variation of ZT value. So, you can look at a maximum ZT value which one can see in the scooterite is around 1.7. Okay. Now, come to two-dimensional material. There are various two-dimensional material, and these two-dimensional materials are basically based on the conventional material, like PBT is one conventional material, and then you have a two-dimension PBT and structure with PB 1 minus X, europium X and tellurium. Okay. Similarly, there are other the two-dimensional material with this conventional thermoelectric materials, and these are the type of carriers. Here you can see that figure of merit is quite high, and you can have a maximum figure of merit of 2.4. Okay. So, it is quite optimized figure of merit value when we use this quantum well structure. So, now if we see the nanowire, in many cases nanowire, although we have been enhanced the quantum effect, but it has been reported in the nanowires the typical values of ZT is close to 1 or slightly more than 1, and then nano composite, which I discussed in the last class. Okay. So, one typical nano composite is a nano composite BISBTE. Okay. You make a composite of BISBT or a bit complex composite also, which one can make. One can change the atomic fraction of bismuth, antimony and tellurium. Okay. And one can have a bit the variation in the composition of the nano composite, and for different the carrier type, one can see a good variation in the figure of merit. So typically one can see that this is around 1.8 is the maximum one, okay, but in lead telluride nanocomposite one can see a reported value of around 2.2, and silicon germanate based nanocomposite also people have prepared, and a typical value of 1.3 is found. So now what we conclude from all this discussion, we conclude that the several materials which are used as the thermoelectric materials, okay, after a lot of the engineering of materials, either you make a composite or you go to lower dimension, okay, or you make a the PGAC kind of structure. So all these materials engineering which are being used for optimization of ZT shows that one cannot have drastically very high value of ZT experimentally so far, okay. So this clearly reflects that one needs to do much more investigation or research as far as materials are concerned. Because if you remember, in my previous class I have shown the theoretical value of ZT have been predicted to up to 8 or up to 10, and then how efficiency varies when we vary this figure of merit, okay. So anything the figure of merit achievable up to 3 or 4 would be extremely the good, okay. So a lot of researches are going on optimizing the material properties, designing materials, okay, and to get the optimum material for a good thermoelectric generator, okay. Nevertheless, people have started using this thermoelectric generator or the concepts in various devices from long time, okay. So one particular thing which came in 1960s 1970s when NASA had employed this known as radioisotope thermoelectric generator or RTG devices. What is radioisotope thermoelectric generator? Radioisotope thermoelectric generator are basically a thermoelectric generator where a radioisotope is used. So what is the role of radioisotope, like polonium PO or plutonium PU? Okay, these are the radioisotopes which people have used. So what are the role of these radioisotopes? The role of these radioisotopes is that we know that whenever we have a radioactive material, it decays, okay. This very basic nuclear physics, that it decays by alpha emission, beta emission, gamma emission, etc., and then it goes to another daughter nucleus and so on and so forth, okay. During its decay process, it actually generates heat, all right. So this heat can be used to create a thermo EMF using a thermoelectric generator device, okay. You will wonder that this type of the use of this type of RTGs was done in 1960s 1970 by NASA, when in the Voyager the spacecraft, they have used a very small thermoelectric module which carries an RTG, okay. It basically carries a small radioisotope source which gives the temperature, little bit of temperature, and it generates the power, okay. And the advantages of this is that, as the radioactivity depends on a quantity which is half-life. Half-life is basically the life by which a radioactive element decays and it becomes half of its activity, okay, typically. And depending upon which radioisotope is used, one can say that, okay, the half-life of this particular radioisotope is for say 10 years, or half-life is say 30 years, 40 years, 50 years, okay. So now if I want to use my spacecraft, this particular TG devices, I can plan it beforehand, because I know that the source will work till say 40 years. It will not reduce, this activity will not be reduced. Okay, or its activity will become just half when after 30-40 years. So I can very reliably use this particular radioisotope, in the thermoelectric generator module inside the spacecraft, and that is what is going on. Okay, and it almost, of course, when its activity decreases, the heat generated by the radioisotope is also reduced, and therefore the efficiency of the device or the power output of the device reduces. But that is, one can calculate it beforehand, how much time one needs in a spacecraft, and it keeps the power output very, very reliably. Okay. So those advantages I have already discussed in my first class. Okay, and then people have also used these RTGs to make small batteries. Okay, very small source was nuclear source or radioisotope source was made in order to make small batteries. Okay, and then they were used in the pacemaker, because they just generate, because of very small amount of heat difference or temperature difference or very small amount of heat, it gives some milliwatt amount of power. All right, and therefore one can use it reliably. However, there is always an issue of radioactivity, and that's why when people have learned the lithium ion batteries and other, which we will discuss in later modules, then this particular idea of making batteries for pacemaker was was no more accepted, but it was been demonstrated that how one can use these small RTG batteries for generation of very small amount of power. So it is not only the generation of small amount of power, one can have large number of RTGs. Okay, and that is possible, that is the reliable or useful when we consider remote place. All right, the place which is very cold, like in Russia, there are many places which are very cold and very dark. You do not get sunlight, so you cannot use even solar power reliably. All right, so the army was given lot of RTGs to lead some of the lighthouses. So it was, you can see that these RTGs were made in a kind of bulk form, and it is actually made as sort of a power generator. Okay, small power generator, but they are good enough to, the for the lighting purpose. Okay, which is required. Okay, so this is one particular application of thermoelectric generator. Another important application is just use the natural heat sources, say biomass. Okay, so you can see a kind of lantern which people have demonstrated. It was just the considering the biomass, small amount of the biomass which can be ignited, and then it can produce some power or some heat, and use that heat. Okay, and then you can make a lantern. And another very interesting the application of the thermoelectric generator in very small scale is using the heat generated from a biological specimen. Okay, suppose human being. Okay, so one can have a shard something like this. Okay, where one can have several thermoelectric modules. All right, very small thermoelectric modules can be inserted. So what happened, and whenever we we do some work, we produce heat. Any biological object produces heat, or any kind of inner biological activities, okay, it also produces small amount of heat. So one can have a small amount of power generator using these modules, which are just inserted into the shaft. Okay, so suppose the biological activity of that particular organism is reduced, one can get an indication, because the power generation in this thermoelectric generator module, which are connected with this biological specimen, are also reduced. But interesting is that just using the natural heat source, that is the heat source of the body, one can have a very good small device. Okay, one can also think about a very large device. This was something like, the solar cell, which we have already discussed, and the solar panels which are being used. Okay, so in the large scale devices, thermoelectric generator, this is called solar thermoelectric generator or STEG, where you can see this is a typical design, and this is the solar irradiation which is falling, and there are some reflecting mirror, and then heat collector here, some selective absorber here also, and this side also, this side also. What are the role of these instruments? The role is that when solar radiation falls, it actually concentrates solar radiation, sort of concentrator, solar radiation concentrator, and this solar radiation concentrator actually generates a heat. Okay, so one can also create a cooling, the side. One can have the heat produced by solar radiation which is being concentrated, and then one can also make a small, the generator. Okay, something like which you can see that the photovoltaic module. And these are important because in many places on earth there is hardly any sunlight. Okay, so you have to use either the conventional power sources. If you do not have these power sources, and also you don't have any chance to generate the photovoltaic power source, then one needs this type of the modules which are based on STEG. Okay, so another interesting application is in automobile. So if you look at typically one automobile, I can say that this is 100% of fuel energy of an automobile, and 25% is basically used in engine output and alternator. Okay, 5% energy is lost in frictional losses in automobile, 30% is lost in the coolant losses, 40% are lost in the exhaust gas losses. So this particular issue I discussed in the introduction section. In an automobile, okay, how much energy is the continuously being lost? This heat energy can be used, okay, using a thermoelectric generator, and one can power the devices inside the automobile, like powering AC, powering heater. Okay, so one need not waste the battery which is used, but one can use these thermoelectric devices using the lost heat from the automobiles, and then use them for powering the electrical appliances. So let us now summarize whatever we have studied so far about thermoelectricity and thermoelectric generator. If you look at what we have studied, we have started with basics of thermoelectricity, and we have discussed about Seebeck effect, okay, how the temperature difference can generate a voltage, and there is a quantity which is known as thermo EMF, which is defined from the basics of thermoelectricity or from the Seebeck effect. And then we have seen Seebeck effect in semiconductor. Why semiconductor? Because one has to optimize parameters like power factor and figure of merit. Okay, that is what we have seen. One can optimize in case of semiconductor because it depends on Seebeck coefficient, it depends on electrical conductivity, it depends on thermal conductivity. So considering all these the physical quantities, one can see that an optimization can be done in semiconductor or doped semiconductor, so that the device or thermoelectric generator device can be made out of the semiconductor. Okay, we have also discussed about thermoelectric the module and its efficiency, how one can define a thermoelectric module, and considering it is connected to a particular load outside, one can also calculate the efficiency, and what we have seen from the efficiency calculation, one can also get the expression for figure of merit from the efficiency derivation. Okay. And then we have discussed several material aspects. So, some materials are like conventional thermoelectric material, okay, which are mostly chalcogenides, okay, bismuth telluride, lead telluride, silicon germanide, etc., which are used at different temperature ranges, and these were actually studied for quite some time, for several decades, okay. And then what we have seen, that people started thinking about enhanced figure of merit in nanostructured material, okay. So, lowering the dimension, changing the density of state, tuning the electrical conductivity, tuning thermal conductivity, etc. So, in nanostructured material, what we have seen uh, a nano wire kind of structure, we have seen nano composite kind of structure, and then of course two-dimensional nanostructure, okay, or two-dimensional well or quantum well structure. We have also seen a PGSC material, which actually tells that its thermal conductivity should be like glass, okay, and electrical conductivity should be like crystal. Okay, and what we have seen, that schutterides and clathrodides are two classes of material where one can see some features of PGSC material. Okay, and then we discussed about thermoelectric generator devices as a whole, and one can have series of small modules, and then one can see how much power can be generated when we combine all the modules and make a thermoelectric generator device and get the output power. Okay. And finally, we discussed applications of thermoelectric generator.